Hello, a very good evening to all of you. Okay, my name is Shubhajyoti and I'm going to be starting off with a new chapter that is for ICSE class 9. The name of the chapter is Rational and Irrational Numbers. Okay, we'll be covering this like concept and chapter probably within two classes. Okay, so without any further ado, let's head on to straight to the chapter. First thing is what we are going to be covering in this chapter. We are going to be covering why are we learning rational irrational numbers, what the introduction, rational numbers, examples, what are rational number, irrational numbers, examples, then surds. Okay, then after surds, example, everything. So rational, irrational, and surds. These three are the main three like types of concept that we are going to be covering in this particular section. Okay, so we'll be doing all the examples in practice so that we have a clear ideology of what we are about to do. Okay, let's begin. Okay, next, this particular chart is very important for all of us to understand what are this. Okay, okay, so let's start off. See, this is a classification of number system. This consists of entirety of everything, whatever numbers there are and everything. This particularly is known as classification of number system. Okay, so if you want to find out what is the first bit sense of expansion that can be done, first is what is imaginary number and what is real numbers. Okay, so the first type of classification that we find out is imaginary and real numbers. So if I give you an example of an imaginary number, it is any number that cannot be plotted on a number line. Not only plotted number, but cannot be even imagined. Okay, like if I say minus root 7, the minus is inside the root. Okay, so this, if I say minus 10, okay, so minus, if it is inside a root, it becomes an imaginary number. We cannot do anything with this number. Okay, this concept is going to be covered in class 11, not now. Okay, so we'll be focusing on the right hand side. Okay, that is what are real numbers. In real numbers, basically we have two portions. One is rational numbers and one is irrational numbers. Okay, we'll be learning everything there is to know about these two in this particular chapter only. Okay, so rational numbers is denoted by capital Q. Irrational numbers are Q naught. So it's a Q and a dash on top of it, Q naught. Okay. Now, inside rational numbers, there are integers and non-integral rationals. Okay, integers, we all know what integers are. Integers are divided into three portions: negative, zero, and positive. These positive integers are what is known as natural number. Okay, so when we add zero with the natural numbers, it becomes a whole number. And when we add all the negative integers, this as a whole comes around to be integers. Okay. So this is the classification of whatever numbers are there. So this is the classification of the entire number system. Let me repeat myself. Imaginary number, real numbers divides into rational, irrational numbers. Rational number divides into integers and non-integral rationals, and negative integers, negative, zero, positive integer. If I say zero, zero is neither positive nor negative. This has to be a case. Zero is neither positive nor negative. Okay, if we positive integers are called natural numbers, natural number plus zero makes us whole number. That is that. Okay, next. Now, why are we learning this? So, firstly, video of what are real numbers. Let us first find the video of what are real numbers. Uh, See, this video is not there in this particular slide. Oh, no problem. Real numbers, we have already covered what are real numbers. Real numbers are numbers that can be plotted on the number line. That's it. Let's not go very deep into this because this concept is already well and truly done. Next, we come into rational numbers. Definition. A rational number is any number that can be expressed as the ratio of fraction of two integers, that is p by q. Okay. Before going into the nitty-gritty of this particular concept, let me explain it to you. So, rational numbers q is denoted by small p by capital by small q, where p and q are integers and q cannot be equal to 0, because if we have a 0 in the denominator, then that entire thing will be undefined and it cannot work. Okay, so if I say 0 by 1, is this a rational number? Yes, it is a rational number. If I say 1 by 0, is it a rational number? No, because when 0 is in the denominator, it becomes undefined. Okay, that is exactly what we have understood. Next, now 4 by 2 is rational numbers because both 3 and 4 integers and 4 is not 0. Okay, here 4 is not 0 term is incorrect. It will be 3 is not 0. The denominator, we are going to focus on denominator. Okay, next, minus 5 by 2 is also rational numbers because minus 5 and 2 are integers and 2 is not 0. Perfect. 7 is a rational number because it can be written as 7 by 1. So if I say there is a number called 7, 121, 34 by 70. Are these all rational numbers? My first guess is yes, because denominator is divided by 1. Denominator is 1 in all of this case, and this is nothing but 2, which can be interpreted as 2 by 1. So yes, all of these three numbers are good rational numbers. Next, rational numbers can be positive or negative. We have already answered. If I have a negative integer, no, minus 7 by 3. So this is a negative rational number. That's it. When writing as decimals, rational numbers can be either terminating or repeating. Let us understand what are these. Okay, terminating decimal. If we have a rational number, but the denominator is something like 5 by 4, 7 by 10, 3 by 5. When we have the denominator as a multiple of 2 and 5, it will be terminating. Terminating means that the answer will be in decimal, that is true, but it will end. It will end. Let us take an example for all of these. The first one, we are dividing 5 by 4. So 1.25. That is it. Second one, 0.7. Third one, 0.6. Okay. In all of the three cases, we can see that the numbers are getting terminated. Okay. So this is what is known as terminating decimals. Okay. Now, for non-terminating decimal, anything other than the two denominators multiple, if it is there, like for example, if I write 7 by 3 or 6 by 7 or 9 by 13. Okay, the denominators are not the multiples of 2 or 5. Okay, so let's find out for this one. So 3 will be, let's divide this. Let me show you first this. 1 second. Seven by 3, right? So 3 divided by 7. 7 ones are, so sorry, 7 twos, 3 twos are 6. So 1 decimal point 0 0. This will be 3. 9 minus 1 0. Again 3 9 minus 1 0, and this will continue till infinity. This will not be terminating, this won't end. So 7 divided by 3 will actually give us 2.333333, and it will continue. So to make it short, we are going to write it is 2.3 bar. Okay, so this is what is known as non-terminating decimal. It is not going to terminate. Okay, now let's head on for the next example. So if I write something like 7 by 9, okay, 9 divided by 7, 0 point, okay, 70, 77, that is 63, again 77, so it will move on till infinity. So 0.7 bar. Okay, this repeating numbers we will write with a bar on top of it. That is what is non-terminating decimals. Next, let's start off with irrational numbers. Okay, now what are irrational number? I think there is a video regarding this. Let's give it a watch. What are irrational numbers? Okay, let's watch it.
Now we know that square root of 2 is an irrational number. If you use a calculator to calculate the value of root 2, you will get something like 1.4142135 and so on. This value that you get is actually non-terminating. It is never ending. Also, you will not find any pattern in the digits after the decimal. Hence, it's also called a non-recurring decimal. There is no pattern that occurs again and again. These kinds of numbers are called irrational numbers. Consider square root of 3 for instance. You will get its value as 1.732050 and so on. Even this decimal is non-terminating and non-recurring. So root 3 is also an irrational number. You can try calculating the values of root 5, root 6, root 7 or root 8. You will find that all of them result in non-terminating, non-recurring decimals. But wait, root 9 equals 3. This is a rational number. Yes, root 9 is not an irrational number. In fact, square root of any perfect square will be a rational number. But the square root of any number which is not a perfect square will always result in an irrational number. Here's the interesting part. If you know these 2 points well, you can even form an irrational number by yourself. Let's see how. We have to form a number which does not end and does not repeat any pattern. Something like 2.010010001000001 and so on. Here, the number does not end and is also non-recurring. This means that there is no pattern that repeats forever. You can even have a number like 15.2349, 449, 4449, 44449, and so on. This is also irrational as it is non-terminating and non-recurring. Where does this concept help us? Say you're asked to find 2 irrational numbers between 1.23 and 1.25. Remember, 1.24 is incorrect as it's terminating. We need a non-terminating, non-recurring decimal. Yes, we know that 1.24 is between these 2 numbers. After 1.24, we can start writing 01, 001, 0001, and so on. That's one irrational number between these 2 numbers. Again, let's write 1.24, and this time we write 02, 002, 0002, and so on after it. That's your second irrational number. So to find irrational numbers between 2 numbers, just write a rational number between them and then add non-terminating, non-recurring digits after it.
Okay, we've understood what this is all about. Let's continue with the chapter. Now we have already understood what is the definition of irrational number. An irrational number is a number that cannot be written as a fraction of two integers. In other words, it cannot be expressed in the form p by q. Irrational numbers are numbers whose decimal expansions goes on forever without repeating or terminating. Okay, so they are, to be very precise, we can say these are fractions which are going to be non-terminating and non-repeating in nature. That's it. Okay. Examples are root 2, root 3, root 4. Root 4 is actually 2, which is actually a rational number. So we will be going like, always remember, root 4, root 4 is actually root 2 square, which is 2, 2 into half, that is 2 to the power 1, which is actually nothing but a rational number 2 by 1. Okay, but in case of root 5, the same will prevail. Root 5 is another example of an irrational number. Okay, similarly, root 2, root 3, pi, these are all irrational numbers. Okay, let's continue. Next, irrational numbers have non-terminating, never ends, non-repeating decimal expansions. Okay, so like this, all of this we have done in the last portion of the slide. This one, the root 2 will keep on continuing, non-repeating. Okay, similarly for the others. Next, we have another video about why irrational numbers and why do we need them. What are irrational numbers and why do we need them? Let's watch the video first to have a good understanding. Let's find it out.
To prove the existence of irrational numbers, a right-angled triangle ABC was considered. The triangle was such that these two sides equal 1, and the length of the hypotenuse was supposed to be found out. The Pythagoras theorem was used to get AC squared equals AB squared plus BC squared. AB and BC both equal 1. Substituting those values here, we got AC squared as 1 squared plus 1 squared, which equals 2. If AC squared is 2, AC will equal square root of 2. And Hippasus said that this is an irrational number. But why? How did he prove it? He used an indirect proof, and this is how he went about it. He said, let root 2 be a rational number. It implies that root 2 can be written as p by q, where p and q are integers which do not have a common factor. P by q is in its simplest form. How do we eliminate the radical now? To eliminate the root sign, we square both sides. So 2 equals p squared by q squared. Transposing q squared to the other side, we got p squared equal to 2q squared. This gives us a very important result, and let's call it our first equation. What does this tell us? We know that 2 multiplied by anything is even. So the first equation tells us that p squared is even. It also means that p is even. That's because if the square root number is even, the number has to be even. 2 squared is 4, 6 squared is 36. If the square is even, the number is also even. So let p be equal to 2a. An even number is always in the form 2 multiplied by something. Substituting this value of p in equation 1, we get 2a the whole square equals 2 multiplied by q squared. A can be any constant. Opening the brackets, we get 4a squared equals 2q squared. Cancelling out the common factors, we get q squared equals 2a squared. Observe the right hand side. It's 2 multiplied by something, which means that q squared is also even, which means that q is also even. Wait, this gives us an interesting result. It tells us that p and q are both even numbers. This simply means that 2 is a common factor of p and q. If both are even, they will surely have 2 as their common factor. But look at what we assumed. We assumed that p and q have no common factors. So this is a contradiction to our hypothesis. Hence, root 2 is not rational, and numbers which are not rational are called irrational numbers. We can say that root 2 is an irrational number and cannot be expressed as p by q.
So this is how we are going to be proving for not only root 2 but root 3, root 5, anything. Same explanation, same thing we have to write down in the copy. Nothing else, nothing different. Okay. Now we have something called surds. Okay, we'll be doing surds when the time comes. First, I will just tell you about the definition of surds and we'll start from that only. Okay, so a surd is an expression that involves root, especially square roots, cube roots, or any higher roots which cannot be simplified to a rational number. In simple terms, a surd is an irrational root. That's it. For example, root 2 is a surd because square of root 2 it cannot be simplified to a rational number. Root 5, root 3 are also surds. Okay. So why are we requiring surds? What is the importance of surds? If that is the question. Second. Now we have to understand what is the concept of rationalizing. Okay. So let's so see, we have something. This is for 1 by root 2. I'll doing it for 1 by root 5. Okay, something like this is present. We cannot write this down. We cannot write this down in what? In fraction form, but less than fraction form. We have to find some way to convert this denominator of root 5 into the numerator. At least we have to do that. So what we'll have to do? We'll multiply both sides by root 5 into root 5. So it will not change the equation. Okay, then what we'll do, it is actually nothing but root 5 into root 5 into root 5, that is root 5 by 5. Okay, so this is how we are converting from the denominator of root 5 to root 5 divided by 5. Okay, so we do not have any longer an irrational number in denominator. That is the basic like functionality of what is rationalizing. Okay, so now this is whatever is written in your book. Let's give it a quick read. So imaginary number, real numbers, we are very okay with that. What are imaginary and real numbers? If x is equal to 4, root x, so root over minus of any integers is actually an imaginary number. Okay, so root 4 is a real number, but minus root 4 is an imaginary number. So minus root 5 is imaginary, but root 5 is real. Okay, so starting what are rational numbers? Irrational numbers, we are very okay with this now. Integers, non-integers, negative, 0, positive, rational number, whole numbers. I think this is more or less done. Next, a number which cannot be expressed by, okay, we have done off with rational numbers. What are rational? P by Q, it is written A by B here, where B cannot be 0 is a rational number. Done with this. So it is a rational number. Oh, we have already covered this. Now, first sum. Which of the rational numbers 3 by 5 and 5 by 7 is greater? And inside 3 rational numbers between 3 by 5 and 5 by 7. Okay, let's solve this. Okay, so we have two numbers 3 by 5 and 5 by 7. Okay, firstly, we have to understand which is greater. There are two steps of finding this out. One is when we are multiplying crisscross. Okay, so 21 and 25. So 25 is greater. So what was 25? 5 by 7 is greater than 3 by 5. This is method number 1. Method number 2 is what? We have to make the denominator same. So 3 by 5, 5 by 7 into 7 into 7 into 5 into 5. So what do we have? 21 by 35 and 25 by 35. Now we know this is greater, but this is actually what? This is actually 5 by 7, which is greater than 3 by 5. Okay, so by this, any one of these two methods, we have realized, so 5 by 7 is greater than 3 by 5. If also this is not even done by you, let's divide it, let's find one other method. So 3 by 5, if I divided 0.6, similarly 5 by 7, if I divided 0. This is 7, so 49, 101, 7, 30, this is 4, 28, 202, 14, 6. Okay, so it will give us what? 0.7142. Obviously 0.7142 is greater than 0.6. So any of these three you can do it, no problem. Okay, so first part of the question we have solved. Okay, so 5 by 7 is greater than 3 by 5. This is done. Now insert three rational numbers between them. This is very easy. See, 3 by 5, 5 by 7. First rational number is, we are going to add the numerator at the denominator. That's it. So 3 plus 5, 3 plus 5 by 5 plus 7. What do we have? We have 8 by 12. Okay. Divided by 4, 2, 4, 3. So now we'll write it down. So 3 by 5, 2 by 3, 5 by 7. Now average of these two, 3 plus 2, 5, 5 by 8. Average of these two, 5, 6, 7, 7 by 10. Okay. So three rational numbers between them are 3 by 5, 5 by 8, 2 by 3, 7 by 10, and 5 by 7. That's it. Okay. And this is the ascending order as well, because 3 by 5 is the lowest and we are going from here to here. Okay. Next. Okay, so we have done this as well. They have used a different method, but every method is valuable and it can be done. Now, properties of rational number. The sum of two or more rational numbers are rational number, obviously. The difference of a rational number is always a rational number. Let us take an example. Sum of two rational numbers. So one is 2 by 3 and the other is 1 by 6. So 6, 4 plus 1, 5 by 6, also rational number. Difference. Also a rational number. The first two are done. Product. 2 by 3 into 1 by 6, 2 by 18, or 1 by 9, also a rational number. But division of a rational number by a non-zero rational number is always a rational number. Okay, what is that? So 2 by 3 when divided by anything other than 0, 1 by 2. Okay, so 2 by 3 reciprocate 2 by 1, so 4 by 3 rational number. If 0 is present, obviously is multiplying by anything divided by 0 in the numerator, okay, will give us an undefined number. That is the reason why only in case of division we have to have non-zero rational number is always. Okay, sure. Next, decimal representation of rational number. We have already done this. We have been doing it since class 7. Okay, now without doing actual division, find whether each of the following is terminating decimal or not. Okay, multiple of 2 and 5, yes, terminating. 2, yes, terminating. 2, terminating. Okay, without even doing anything we have found it out, but let's give it a shot. 7, by 50. Okay, divided by 5 it is coming 10, divided by 5 it is coming 3, 15, 15, 16, 17 to 20, 3.4. Answer is 0.34. Okay, so we have done this. Next one, 7 by 8 divided by 2, 4, divided by 2 is 3.5, divided by 2 is 2, divided by 2 is 1.75, again divided by 2 is 0.875. Done. Last one, 2372. Okay, divided by 2, 36, divided by 2, 1, 1.5, divided by 2, 18, divided by 2, 5.75, divided by 2, 9, divided by 2, 2.675, divided by 3, 3, divided by 3, 0.891. Let's leave it at that. Last 0.2, 29 is 9, then 7, 8, 9, 21, 7. Okay, so all of this are coming out to be numbers that are going to get terminated. Okay, so we have done this. Now comes irrational numbers. Okay, irrational numbers, we have already familiar with this concept now because we watched the video, we've understood what is irrational numbers. Now, representation of rational irrational numbers in case of number lines. This is a fresh new concept. Okay, first we'll not be going forward with this particular concept today only in class. Okay, one second. Okay, so I'll play a certain kind of videos. First portion, I'll be playing some videos, and after understanding what is this, I'll be playing the entire video again. Okay, I'll be playing the entire video again in the next class so that we have a more or less idea about what is this, because this is the new concept that is going to be present in class 9. Okay, we have done like number line in integers, number line in rational numbers, but irrational number lines we haven't done till now. Okay, this is something that is new. So I want you to watch this video first, this first video, the entirety of the first video, and understand what is this. Okay, I'll be playing just one video of understanding what is number line and how to plot rational and irrational numbers on number line. Okay, one second. Okay, then tomorrow I'll be starting off with this video only. Okay, after watching this video, we'll be seeing videos how to plot root 2, root 3, root 5, and from there on, we'll understand how to like find for a number line any irrational numbers. Okay, let's give this video a shot.
How do we represent irrational numbers on a number line? Numbers like root 2, root 5, they are non-terminating and non-recurring. It means that we cannot calculate its numerical value and plot it. It's not difficult at all if you understand just one simple concept. Consider a right triangle OAB. Let these two sides be equal to 1. Since this is a right triangle, we can use the Pythagoras theorem. In this triangle, OB squared will equal OA squared plus AB squared. These two lengths equal 1, so we get the right hand side as 1 squared plus 1 squared, which equals 2. So OB will equal root 2. The hypotenuse will equal root 2. That's all you need to know to understand the plotting of irrational numbers on a number line. That's it. We found the length of an irrational number. The only thing we need to do now is plot this length on a number line. We will see that in the coming videos.
Okay. So in this particular class, we have learned about, we have done till this slide number 35. So from 36 to 70 will be going on and be doing tomorrow. Okay. So this particular session was all about what was the different type of numbers in number system. We have started off with every number in the entire universe, split it into two. One is imaginary and one is real. In then imaginary, let it be that. Examples of imaginary: root over -3, -4, anything under root with a minus is going to be imaginary. Okay. Then comes real numbers. Real numbers can be plotted in a number line. Okay. Then after real numbers comes two part. One is rational numbers and one is irrational numbers. In rational numbers, there are again two parts. One is terminating, one is like terminating rational numbers, and one is non-terminating rational numbers. Terminating rational numbers, non-terminating, we have done everything. Now, in case of rational numbers, inside there are integers. Inside integers, there are three: negative integers, zero, and positive integers. Okay, so this was the entire gist of what we have learned today. In the next class, we'll be learning about how to plot everything on a number line. We have already learned how to plot integers in a number line and rational numbers in a number line since the last classes. Now, in this particular class, the next class, we'll be doing about how to plot this irrational numbers on a number line using this concept. What? Hypotenuse, base. Simple will be using Pythagoras theorem. Okay, and a protractor and a scale to understand what these concepts are all about. Okay, I hope you had a good class. Do please watch this video first before traveling to the next portion. Hope you had a great day. Bye bye, guys.